Hey everyone! Ever heard that a butterfly flapping its wings in Brazil could cause a hurricane in Texas? Sounds wild, right? Welcome to the mind-blowing world of chaos theory, the science of unpredictability. Chaos theory explains how tiny changes can lead to immense and unexpected outcomes. But don't get it twisted, chaos isn't just randomness. It's rooted in strict mathematical laws. Today I'm breaking down the core concepts of chaos theory using real-life examples. First up, sensitivity to initial conditions, the butterfly effect. Picture a row of dominoes lined up. Give the first domino a tiny nudge in one direction instead of straight forward. The entire pattern of how they fall could change drastically. This is sensitivity to initial conditions. A small change at the start leads to massive differences in the final outcome. This is famously called the butterfly effect, coined by meteorologist Edward Lorenz. In the 1960s, Lorenz found that tiny rounding errors in weather models led to completely different forecasts. That's why long-term weather predictions can be so unreliable. Next, let's talk about deterministic yet unpredictable behavior. Chaos is not random. It's deterministic, meaning it follows precise rules. But it's so complex it looks random. Take a regular pendulum. You can predict exactly where it'll swing. But add a second joint, and suddenly it behaves like it has a mind of its own. This is deterministic chaos. You'll see the same thing in turbulent rivers, traffic patterns, and even the flow of air over an airplane wing. Now let's dive into fractals and self-similarity. Fractals are patterns that repeat at different scales no matter how much you zoom in. Look at this. This is the famous Mandelbrot set, a mathematical fractal that never stops repeating itself at smaller and smaller scales. But fractals aren't just in math, they're everywhere. From the branching of trees and blood vessels to the way lightning forks through the sky. Onto strange attractors, the fingerprints of chaos. If chaotic systems are unpredictable, do they have any structure at all? Yes. Enter strange attractors. These are patterns that chaotic systems tend to follow but never exactly repeat. Unlike a swinging pendulum that always returns to the same point, chaotic systems trace out complex, non-repeating paths. The Lorenz attractor is one of the most famous examples. This pattern emerges in weather, electrical circuits, and even brain activity. Now, nonlinearity, the power of tiny changes. A linear system is like turning up the volume on your music. Doubling the dial doubles the sound. But nonlinear systems? They're trickier. Take predator-prey dynamics. A small increase in rabbits might lead to a huge boom in foxes, which then collapses when the rabbits run out. The effects aren't proportional. Finally, feedback loops, chaos in action. Ever heard that annoying screech when a microphone gets too close to a speaker? That's a feedback loop. A small sound gets amplified, loops back, and explodes into chaos. This same idea explains how climate change accelerates. Melting ice exposes darker ocean water which absorbs more heat, causing even more ice to melt. And believe it or not, even social media uses feedback loops. The more you engage with certain content, the more the algorithm feeds you similar content, reinforcing your beliefs and creating digital echo chambers. So there you have it. Chaos theory shows us that even the smallest actions can have huge, unpredictable consequences. It's a wild, fascinating world out there, and I hope you enjoyed this dive into the science of unpredictability. If you liked this video, hit that like button, share it with your friends, and don't forget to subscribe for more mind-bending science content. Thanks for watching.